So we're going to learn about the instruments we use to measure mass. Now, I call them instruments because that's what we use in a lab. They're very finely tuned, or supposedly we can get very accurate results with these tools, so we call them instruments. And if you notice, I said mass, not weight. So what's the difference between mass and weight? Well, weight is due to gravity. So the Earth pulls on everything and exerts that force. And so something like this rock, this is actually galena, it's a lead ore, has a certain weight. But if I went to Mars or if I went to the moon, the gravity would be different. So the weight of this rock would be different as well. So we need a way that we can talk about how much stuff there is in this rock anywhere in the universe. And we use mass for that. So on Earth, and of course that's where we are, mass and weight are the same. 1 kilogram is mass and it weighs 1 kilogram in weight on Earth. If we took this rock, which we're going to find out how much it weighs, to Mars, then it would weigh differently, but its mass would be the same as it is on Earth. So to be correct, we say we find the mass of this rock. So how do we find the mass? We use a balance or a scale. And so let's see how we can use those. And I have 3 of them set up, and we're going to see how we use each one. And if I turn it on, you can see it will weigh up to 600 grams, and you have to give it a second to warm up. It's reading in grams, and you can see the decimal point is telling you that it can read down to the 10th 100th of a gram. So if I put my rock on here, it's easy enough. Boom, it tells me my galena rock weighs 164.13 grams. If I took this rock to Mars, it would weigh less, but its mass would be 164.13 grams, the very same. Now, what happens if we have a container? So here I have a container of ground up galena. How do I get the mass of the galena without getting the mass of the container? Well, to do that, first what we do is put the container on the scale. And you can see the container weighs 105.15 grams. And then I'm going to hit this button here. It says tare or 0. If I hit that, the scale automatically subtracts that. It says I have 0. And then if I add my material, whoop, I will get a reading. This is a triple beam balance. Triple beam balance because it has 1, 2, 3 beams. And it's used the same way as the electronic balance. Well, it's used for the same reason. It'll get down to the very same 100th of a gram, but takes a little skill in using it. The good part about this type of scale is that there's no power to go out, there's no electronics to go wrong, and 500 years from now, this will still be giving you an accurate reading. So how do we use it? First thing you're going to do is put all the weights to 0. And the scale should end up at the 0 point here. Then you take your sample, here's our galena again, and we put it there. We start with the largest weight. Now 100 doesn't tip it. 200 is too much. So you go to too much, and then you go to back 1. Then you go to the next highest weight. Nope, 10, 20. Make sure it's sitting on the notch. 30, 40, 50, 60, 70 is 1 too much. So let's go back to 60. Then we push this one until we get it to 0. And then we just add them up. 100, 60, 3 point, and now we count the lines. 1, 2, 3, 4, 5, 6. It's kind of right on the 7. So 0.70. That's how we read it. 163.70. If we wanted to do the weight without the container, we would have to weigh the container first and then weigh the container with the material and subtract. You have to do a little math on a piece of paper. Now the third type of scale you might come across is kind of like this. It's a balance that has 2 plates on it. The plate on the left is the one where you're going to place your sample to be weighed. Now, just like before, weights start out at 0. And see, this one only has 2 beams. So you'd slide the first one up to the point at which it's 1 too heavy, and then slide it back. And then slide the smaller one until it balances. And then we get about the same thing, 164.1 grams. Now, what happens if we have something that weighs more than 200 grams? What do we do? Like, for instance, this. No, nothing we do is going to be able to balance that. So what we need to do is have a separate weight. This weight is 200 grams. I'm going to put 200 grams here. And then, as I go up to, whoop, 1 too many, still too many, 1 too many, slide that forward. A little more, we got to get that 0 on the line. And now we've got 160 plus 200. So that's 369. And we have to estimate that looks like 9.2. So 369.2 grams is what this whole thing weighs, which means, of course, we have to go back and weigh an empty beaker and subtract out the difference. So that's how we use these 3 types of balances. Let's try a little practice in reading the triple beam balance, see if we can get those right. Okay, let's try a couple of these. So here's one. It's just a picture of a triple beam balance. What would you read this as? Well, I'll give you a second. So here we would look at it as 536 that's 567, and it is pretty much exactly on the 8. So that would be 80. So the weight is 536.80 grams. And that's how you get to the 100th place. Let's try another one. We always start with the largest weight, 200, even though it's in the middle. 290, and that's a 0, so it's not even 291, it's 290 point, and that looks like it's just before the 2, so 0.19, 290.19 grams. Let's try this one, give you a second. Okay, 263 point, ooh, that looks just a little shy of the 5 lines, so it's a 349. So 263.49 grams. That's how I would call these. And now I'd like you to try the ones that you have on your papers, on your sheets, and see how you do on them. They should look like these. Okay? Now, how about volume? We've got several different things that we use, several different pieces of equipment that we use to measure volume. And one of the most useful ones is this. This is called the graduated cylinder. And it's called graduated cylinder because it has graduations on it, markings. Just like, you go through first grade, second grade, third grade, fourth grade, and then you graduate. Well, this goes from 100 to 150 to 200 milliliters, and it becomes a 250 milliliter graduated cylinder. So graduations basically mean levels. Now this graduated cylinder, it has some water in it, and you can see if I hold this up, the water kind of has a sort of thick layer at the very top, and that layer does not go flat. It actually hugs the sides of the cylinder. It moves up on the glass. So how do we read this? Do we read it from the top of that, what we call meniscus? That's the thick layer on top, the meniscus. Do we read from the middle of the meniscus, or do we read it from the bottom of the meniscus? Like, how do we read this as accurately as possible? Well, chemists got together, and what they decided is that they would read this from the very bottom of the meniscus. So the bottom of the meniscus lines up with a line, and you can see here that you would read 22.0. Even though the top of the meniscus comes up to 23, you would read it as 22.0 because we read it from the bottom of the meniscus. So if we can zoom in on this a bit, you can see here you've got a little bit, just about 5.52. We can try to estimate between the lines as best we can. So this bottom of the meniscus is not exactly on 5.5, it's a little higher. So we could get a number that's to the 100th place. That's about as accurate as we can get. And we can measure solids using a technique called displacement. So if we put water in a graduated cylinder and then we add a solid to it, the water level will rise, and the volume of water displaced, pushed away by the solid, is the volume of the solid. It kind of makes sense. So if the water level goes up 5 milliliters, then the volume of that block that was dropped in must be 5 milliliters. And we can call that 5 cubic centimeters as well, because a cubic centimeter is the very same as a milliliter. Good to know. So reading from a pipette can be done the same way. I put the pipette in and I read the level. Let's say I bring this up to the bottom of the meniscus, reads 7.00, and I want to deliver 3 milliliters. I would go from 7 to 6 to 5 to 4, and that would give me exactly 3 milliliters added. So we read from the bottom of the meniscus in any piece of glassware that we're working with. Here are some examples of graduated cylinders with the meniscus for us to practice on. You can see the first one as an example is given for us, and remember, each graduated cylinder might be different. Some are larger than others. So here, this line is 30. This line up here is 50. So that means that each one of these lines is 2 milliliters, right? 2, 4, 6, 8, 40, 2, 4, 6, 8, 50. So that tells us that 2, 4, 6, 8, this bottom of the meniscus is exactly on the 40 line. Therefore, it's 40 milliliters. So what's the scale on this one? Well, let's see. If this goes from 30 to 40, then this is right in the middle must be 35. So then each one of these must be 1 milliliter, and that gives us 35.0. Here's 25 to 35. So how many are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Each one is 1 milliliter. So that gives us 25, 26, 27, 28, 29, 30. That's right on the line, 30.0 milliliters. Don't forget the 0.0. Don't forget to put in the decimal places that we can estimate to. Same thing over here. These are all pretty simple for us. 40, 50. So of course that's going to be 45.0. So try the practice pages and see how you do. When you have finished them, bring them up to me and I will show you what the answers are. You can see how well you did. And if you need to do a little more practice, we have some more practice sheets.